All right, so let's continue on. We did 2A last time, I think, right? From 11.9. Let's just go on and do B. So remember, the goal here is to try to use this formula, the fact that 1 over 1 plus x has this as its power series expansion. So we have to use this fact for both of these parts, including B, the one we're going to work on now. Although in this case, in the last problem we did, we kind of noticed that it looked a little bit like that 1 over 1 plus x, except it had that third power in the denominator, so we had to integrate it a couple times to get it to the place where we needed it to be. In this case, this one really doesn't look at all like that form, right? 1 over 1 plus x. However, what we need to notice is that the derivative of this function really does kind of look like that. So if we take the derivative of the arctangent, remember what that is? Derivative of arctangent of u is? Remember that? 1 over 1 plus x squared, right? We do the interval of convergence. I don't remember doing that, but it would have been the same as the interval of convergence for 1 over 1 plus x. That would have been x less, absolute value x less than 1. We didn't have to alter that. We didn't have to factor anything out of that denominator or anything. So yeah, it would be the same interval of convergence as 1 over 1 plus x. Okay. All right, so yeah, the derivative of arctan of u is 1 over, well, it's actually u prime over 1 plus u squared. So in this case, u is 2x. So in the numerator, we're going to have a 2. And then in the denominator, we'll have 1 plus, and then it has to be the whole thing, 2x quantity squared. There's our derivative. Okay. And so now what we need to notice is that really does match the 1 over 1 plus x pretty closely, right? So we can just use that then as our formula. We can say this is the same as this power series, replacing the x to the n with 4x squared to the n. We'll have 2 times minus 1 to the n times 4x squared to the n. Everybody okay with that? And then remember that, and this isn't really said in the book or anything like that. It's just sort of more of a, if we notice the way that the power series were kind of written before, we can sort of try to mimic that and make it look a little bit nicer. Here we can write this as 4 to the n. And in fact, 4 is 2 squared, so even better than that, since there's already another 2 in there. You could even write it as 2 squared to the n. And then the rest of it x squared to the n, or x to the 2n. And then taking that a little bit further, you have a 2 squared to the n, that's 2 to the 2n, and then there's that other 2 over there. You can actually end up writing this. Maybe nicest looking way would be minus 1 to the n, 2 to the 2n plus 1, and then x to the 2n. That makes sense how we got to that part? Okay, and then interval of convergence. When you're deciding what the interval of convergence needs to be, you just need to look at what was taking the place of the x here, right? And then ultimately right there. That number, whatever that is, whatever that quantity is what needs to be less than 1 in absolute value. So the radius of convergence here, what you do is just take that thing that's in that spot where the x is, 4x squared absolute value, has to be less than 1 for convergence. And that, again, comes directly from the geometric series condition for convergence. And then we can divide both sides by 4, We actually don't even really need the absolute value just yet because it's squared. And then we take the square root of both sides. We get x, absolute value must be less than 1/2. So that's the radius of convergence on this one is 1/2. The interval of convergence, this is centered at 0. So if you want the interval of convergence, it's just negative 1/2 to positive 1/2. And the reason that we don't need to check endpoints in this case, we don't need to check them, by the way, is because, again, this is coming directly from a geometric series. If you remember what the condition for convergence of a geometric series was, the absolute value only makes it positive 1. No. So when you take the square root of, when you solve the equation x squared is less than 1/2, taking that square root, really, the square root of x squared is actually the absolute value of x. So you definitely need to have you keep the absolute value on there. And then interval of convergence is, remember that a power series is only going to converge in both directions a certain distance away from its center, right? So this is definitely going to have a negative 1/2 on there. And it wouldn't even make sense to put the negative 1/4 because you can't have x squared be equal to a negative. That's why we put the absolute value bars in there instead. Okay, so yeah, that's right. R has to be less than 1 for a geometric series to converge, and there's no including 1 in that. It definitely does not converge when it's equal to 1. That was something that we've already seen. So we don't have to worry about endpoints here. We can be sure that it's not going to converge at the endpoints. Okay? At least for this one. Now, I have to make one small caveat about that because what we have just done here, in fact, I got to remember that. What is this the power series for right here? What is that the power series for? No, that's not the one for Arctangent. What did we just find this for? Yeah, we found this for this function here, right? The derivative, this one. Okay. So is that really what we're looking for, though, according to this question for this problem? No. But it's certainly going to help because that is the derivative, right? And so if I want to find the power series expansion for f of x, not f prime of x, that would have to be the integral of this thing here, right? The integral of this function right here, right? But we just said that that function is the same as this power series, right? So we can replace the function with the power series now. Because they're equal. We just said they are, right? The power series and the function are the same thing. Okay, so that's what we need to do. We need to integrate this power series to find the power series for arctan 2x. Okay. Okay, now how do we integrate a power series? Well, remember that it's just a polynomial, and it's, ultimately that's really what it is. It's just a polynomial. So really the only term that we actually care about when we're trying to integrate this thing is this one right there, right? That's the only one that actually has an x in it. And so all we have to do to find this antiderivative is just use the power rule for integration. Okay, so we're going to get, if we do that, so remember the power rule for integration says we have to add 1 to the exponent, so 2n plus 1. Then we also have to divide by whatever number that we just raised that to. So in this case, that's the 2n plus 1. And then since this is an antiderivative, we have to have a plus c on the end of it as well. Okay, so what I was saying about that interval of convergence, well, actually, but I think before we talk about that, let me address how we find that value for c. So note, we can find the c value, by the way. F of 0 for this thing, the function is f of, well, let's just say, what is f of 0? f of 0 is whatever we get when we plug in 0 for the function, right? Arctan 0. Everybody agree with that? 2 times 0 really, but arctan 0. Okay, but that should also give us the same thing when we plug in 0 to the power series, right? Because the power series and the function are the same thing, right? They represent the exact same thing. So we can go ahead and do the same thing with the power series. Plug in 0 for x. And notice, why am I picking 0? Because 0 is the center of this power series, and plugging in 0 to plugging in the center of a power series into the power series always has the effect of just giving you 0 altogether, right? Since this does have a plus c on the end of it, and then all of that stuff, arctan of 0 is, what is the arctan of 0 again? That's just 0. So it tells us that c has to be 0, okay? So that means the power series expansion for arctan 2x must be this thing that we just found, with the c being 0. Okay, now for the radius of convergence, we have it. We can put this right now. The radius of convergence is definitely 1/2, because remember that's that thing on the theorem in the middle of the page for 11.9 on the front. It says that the radius of convergence for both the integral and the derivative of a power series remains the same. The radius of convergence stays the same. Okay. So in this case, we said it was 1/2. Now for this doesn't actually ask for the, oh, actually it does ask for the interval of convergence, so we have to think about that. So this is what we have to kind of worry about for the if you have to take an antiderivative to get back to the function that you started with, which we did here, right? We had to take the antiderivative of this power series right here, right? And that's what we got. So taking an antiderivative, unfortunately, can potentially have the effect of adding an endpoint as far as convergence is concerned. Okay, why is that? Because if you look, by taking that antiderivative, what did we have to put in the denominator? We had to add that thing in the denominator, the 2n plus 1, right? Now that is going to have a potential to actually all of a sudden include one of the endpoints for the interval of convergence. Okay, so unfortunately, when you take an antiderivative to get to your final step, your final answer here, you then actually do have to check the endpoints for convergence. Okay, if you have to take a derivative, on the other hand, to get to your final answer, then you don't have to worry about that. It's only if you have to take an antiderivative to get to your final power series do you then have to think about what might happen at the endpoints of the interval of convergence. So far, what we have is this. We've got, for the interval of convergence, we know that it has to converge 1/2 away from the center in both directions. So it's like that. But now the question is, would it be okay to put an equal to there in addition to the to the less than, right? So how are we going to do that? Well, let's check the two endpoints. Let's check x equals negative 1/2. So if I plug in negative 1/2, again, I'm plugging it in for x. So I'm going to get, let's see, negative 1/2 right here, right to the 2n plus 1. Let me see if this is going to be. Okay, so what happens here? I can rewrite that as, just trying to think if this is actually going to produce a endpoint that it will be included or not. I guess we can just find out. Okay, now this we can write as -1 to the 2n plus 1 times 1/2 to the 2n plus 1. Notice that I've got 1/2 to the 2n plus 1, and I've also got 2 to the 2n plus 1. So those terms are in fact going to cancel each other out, and then we're going to be left with this. Now, if you look at what's left here, there's that and that, right? Now, let's see what's going to happen to that. When you multiply -1 to the n times -1 to the 2n plus 1, what is that? What do you do when you multiply the same base, right? You have to add the exponents, right? So we're going to get -1 to the, let's say it's going to be 3n plus 1, right? Which is the same as -1 to the first power times -1 to the 3n power. So let's see, what is -1 to the 3n power going to be? If n is 1, we get third. If n is 2, we get 6. If it's 3, we get 9. So it seems that it's alternating between positive and negative, right? In fact, I guess an even better way to do this would be to say this is the same as -1 times -1 to the third to the n. That's a reasonable way to do that. But -1 to the third is just -1, right? And so we get that. And then this can be written as -1 to the n plus 1. Okay, so with all that in mind, then that means when x is equal to -1, if you simplify that series as much as possible, what's going to happen? You're going to be left with -1 to the n plus 1 over 2 n plus 1. Now, what kind of series is that? Isn't that an alternating series? Yeah, and if you check just real quick, the limit as n goes to infinity of 1 over 2n plus 1, that's obviously 0, I think, hopefully. And then if you compare 1 over 2 times n plus 1 plus 1 to 1 over 2 n plus 1, I think it's pretty obvious that that's going to point that way. Both parts of the alternating series test have just passed, right? So now we can actually come back up here and say, well, it seems like it actually does converge on the left endpoint, right, at -1/2. By doing this, again, it was by doing integration to get to this last point, and the reasoning there is because we introduced that term into the denominator, which, again, gave us the potential to converge at the endpoints by doing that. All right, now notice what happens if you plug in the positive 1/2 for this thing. Well, all of this is going to be the same, except that term right there is not going to be there, right? That term would not be there. But if that term's not there, that doesn't really matter much because, look, that term is still there, right? Which still makes it an alternating series, which means that it's actually going to converge on the other endpoint as well. So this one, by doing that integral in the last step, made it converge actually on both endpoints. So just so you know, I know this is probably a bit confusing. Like, well, again, why do we have to do this if we integrate? Well, try to explain why that's the case, because we produce that extra term in the denominator. If you take a derivative to get to your final step, that's not going to happen. So this would not, you wouldn't have to worry about it. All this being said, I'm not going to worry too much about endpoints of convergence for this sort of process, finding a power series by using this particular geometric series formula. In fact, probably just to be clear about that, I'll just ask you for the radius of convergence on these so that you don't have to worry about the endpoints. But just be aware that this is, this is how you deal with it if you're trying to find the interval of convergence for a power series in this way. Any questions about this? If the center was 2, yeah, that's right. If the center was 2, then you would want to find f of 2, and then that would make the whole power series become 0, right? And then whatever f of 2 is in the actual function, when you plug 2 in there, that would be what c is. In fact, if you want to just say that, the c is always going to be f of the center of the power series, or actually really f of the center of the function itself. Because what we're trying to do is find a power series expansion for a particular function. And if you plug the center into the actual function, then that will be exactly what C is. Okay? And that's always going to be the case. Yep, it's a good question. Yeah, because arctan of 0 is 0. That's right. Yep. Because 0 is the center and arctan 0 is 0. That's why C is 0 in this case. It's a good question because I don't know. Sometimes I throw an extra credit question on the test where I'll ask you to center this thing somewhere besides the 0 or somewhere else where it was initially centered or something like that. And if you have to find an integral or do an integral to get to your last step, there's going to be that plus C on there. You're going to have to figure out what that C is. Okay, let's go on to the next example, unless there are any last questions on this one. All right, I'm going to clear this out. Let's do example 3. So what this sort of gist of this whole section is that you can actually use the power series expansion for the geometric power series, this or this, either of those. That's what we're using in this entire section, okay? The power series for both of those functions right there are very important for this section. And so it turns out you can actually do a lot with just those two functions, right? 1 over 1 minus x and 1 over 1 plus x. As long as you have a function that kind of looks like that, or if its derivative kind of looks like that, or if it's antiderivative, even 1 or 2 derivatives are antiderivatives. If any of those look like either of these two functions that I have in the box up here, then you can use this little technique that we're doing here to find a power series expansion. So in this case, the way that we would approach that is that x squared is not really needed in the top as far as like what we need to use for our power series expansion. So let's just rewrite the function like this. Okay, you see what I did there? Now, that's still not quite right. And in fact, you know what? I think I'm going to not do that just yet. I'm going to leave that as a plus because we still need to get rid of that 16, right? So let's go ahead and do that first. So I'm going to factor 16 out of the denominator. And then it looks pretty good, right? And the only thing, well, at that point, yeah, we could just use this one now, right? Don't even need to have the minus minus. And so what this is going to turn into is this, x squared times the power series for the 1 over 1 plus x. And I guess I should say, well, don't forget the 1/16 right there, right? Typically, I gotta write that in the numerator. This is going to be 1/16 x to the 4th over 16, the n. Oh, and I'm forgetting one thing as well. Let me just redo that because this one has the plus sign between it, right? So I forgot to put that -1 to the n on there too. And then we'll have 1/16, and then we'll have the x to the 4th over 16 to the power of n. So let's clean that up a little bit. That's going to be x squared times -1 to the n. I'm going to go ahead and write that as 16 is 2 to the 4th power, right? I'm going to write that as 1 over 2 to the 4th power. And I'm going to write this as x to the 4n. And then 1 over 16 to the n. Well, actually, even better than that, let's write that as 1 over 2 to the 4th to the n power. So really that's going to actually be 2 to the 4n if we want to do that. Okay, so now if we put all this together, we're going to get x squared. Really, a lot of this is just like properties of exponents. How do we do that? How do we deal with those? In fact, let me go ahead and write this as a numerator. We'll have minus 1 to the n, x to the 4n over. Now, if you look at that denominator there, we got 2 to the 4n, and we got a 4 there as well, so that's going to be 4n plus 4. Why is the n in the denominator the last term? In the last term. Oh, because of the n up here, right? That n applies to that denominator, doesn't it? The one I circled in red there. That makes sense? The n that I circled right here, that n has to apply to that denominator right there. And that's 2 to the 4th, and so that has to be 2 to the 4n, right? Doesn't it? Make sense? So then how do we deal with that x squared in the front? Well, remember what this is. This is just a polynomial, right? That means that if I write this out, I'm just going to have x to the, what, the first term will be like x to the 0 power, next term will be x to the 4th power, and then x to the 8th, and x to the 16th, right? This was probably covered a while back, but what is 1 over 1 plus x? Yeah, 1 over 1 plus x is very similar to the power series for 1 over 1 minus x. In fact, the only difference is that that one is a minus 1 to the n. So the minus 1 to the n isn't there on the 1 over 1 minus x. In fact, it says it right there on the worksheet. If you flip it back over, it says example 2 says exactly that, right? 1 over 1 plus x. Okay, so to answer the question about how do we deal with this x squared out front, remember that this is just a bunch of stuff added together. So that really is just a distributive property. You can just distribute this x squared into that power series. And that's exactly what we do. We just multiply it in. So we're going to get that this is actually equal to n equals 0 to infinity of minus 1 to the n x to the 4n plus 2. That's again properties of exponents divided by this 2 to the 4n plus 4. And so that's it. And then to figure out the radius of convergence, again, we come back to this point right here where that is the thing that replaced the x to the n in the power series. So that is the quantity that we need to be less than 1 for convergence. Okay. Again, I'm not doing the absolute value because it's a 4th power. So x to the 4th has to be less than 16. And so x has to be, absolute value of x has to be less than 2. And so the radius of convergence of this thing would be 2, and the interval of convergence would be minus 2 to 2. If you were to graph this power series on your on Desmos, the one I showed you the other day, you would see that it would pretty closely. I mean, again, you would have to approximate the function, but it would pretty closely approximate it up to only on that interval from minus 2 to 2. Anything away from those, the minus 2 to 2 interval, you would just see it act like a polynomial and just shoot off to infinity or negative infinity. Okay. Any questions about that one? Okay, so that's how you deal with rational functions like this, where you have a x something term in the numerator like that, you just sort of push that x whatever power from the numerators, put it off to the side, and then find the power series for the thing that's left, and then just put that x to whatever power back in at the end by distributing it. Yeah, if it was 1 over 1 minus x, if your function happened to match that instead, then you just wouldn't have the negative 1 to the n on there. That's right. All right, I'm going to go ahead and clear this out. All right, so now one other thing, kind of cool thing that we can do with power series here is we can find the values of integrals that would otherwise be impossible to find, or extremely difficult anyway. Now, if I just, back in the section where we were doing integrals and finding all those techniques, if I gave you that integral back then and said find that t over 1 minus t to the 8th dt, that would be incredibly difficult. In fact, I'm not even sure if that's doable at all by any kind of elementary techniques. But if we use power series, then we can actually evaluate this integral fairly easily, in fact, because if you notice, we can rewrite this thing as this. Right? And then by the geometric power series formula, this would be the same as this. And then doing our thing that we just did in the last problem, we can incorporate that t that's out front there into the rest of it, and then so that's going to give us t to the power of 8n plus 1. Okay, everybody clear? So that means the integral of t over 1 minus t to the 8th should be equal to the integral of this power series. So we just said that that's what t to the 8th is equal to. Or the t over 1 minus t to the 8th is equal to. Everybody with me so far? Any questions? And again, the whole reason for this is because now all we have to do to integrate this is just use the power rule. That's again why power series are kind of nice, is because we know that they're just polynomials. All of them are just polynomials. Integrating polynomials is incredibly easy. All you got to do is just raise the power by 1, right? And then divide by that same thing. So this is just going to become 8n plus 2 over 8n plus 2. And then there's going to be a plus c on the end of this thing, because it's an antiderivative. Okay, now in this case, oh yeah, let's do the radius of convergence as well. So to do that, just come back to the this part right here. This is where we produce that power series. That is the quantity right there that needs to be less than 1. And so t to the 8th has to be less than 1 for this to converge. Take the 8th root of both sides, and you get this. So the radius of convergence is 1 in this case. And that's all that they asked for in this problem. All right, now here's a question. Can we find C in this case? Can we find C for this particular problem? Venture a guess? Educated guess? No, that's correct. You can't find C here. So why not? Well, because if you remember, this is a bit of a different problem than the one we did before, right? The problem we were doing before was just finding a power series representation for a function, right? Arctan 2x and then that other one as well. So if you're just finding the power series representation for a function, just that's what you're starting with, you can always find C. As we had seen, C is just going to be f of the center of the power series, whatever that happens to be. This is not the same problem because what were we doing here? We're not asked to find the power series for a known function, right? In this case, we're asked to find the power series for an unknown function because we don't know what the antiderivative of this function is, right? We don't have an algebraic representation of that function. We're being asked to find an algebraic representation for it. The best we can actually do for that is just finding the antiderivative of the power series. This is just a regular old indefinite integral. And so there's no way to find c for any just indefinite integral, right? There's no way to find c for any indefinite integral. So there's no difference here. This is just an interesting way to find an antiderivative. But we always still have to put that plus c on there. Yes, in fact, this is the only way to find any kind of elementary representation for the antiderivative of this particular function. We would not be able to hope to find a nice algebraic representation like in the normal f of t equals some function of t for an antiderivative here. Is there a way to turn the power series back into a function? No, there's not. This is it for what we can do here. All we can do for this particular integral is to find a power series representation for the antiderivative. There's no way for us to go back to find some, normal elementary representation of this function in the normal way. Because there isn't one, in fact. In fact, I think in this particular integral, even if you ask your calculator to do it, it wouldn't even do it. It's like one of those ones that doesn't have an elementary antiderivative. And so the best we can do is to write its power series. But that's pretty good. I mean, if you can actually graph a power series and see what it looks like, and it will be, an accurate representation of the antiderivative of that function, but only on that interval of convergence, right? And so it doesn't even it only does this job on that small region around the center. But remember that we could find the antiderivative for this centered somewhere else too if we wanted to. Any other questions about this one? All right, so I'm going to give you a few minutes to try to work on these problems. On number one should be pretty straightforward, I hope, at this point. Number two, we haven't done one like that, but what I'll tell you on that one is that you can do a partial fraction decomposition on it, right? And when you do the partial fraction decomposition, what you're going to find is you're going to have two different functions, right? And they'll both kind of look like the 1 over 1 minus x or the 1 over 1 plus x function, okay? So that's my hint. Do a partial fraction decomposition on it, and then you'll have two different functions, right? And you can find the power series representation for both of those separately and then just add them together, and that will be the power series representation of problem 2. Number 3 also is a bit tricky. You have to use these ideas that we've been talking about as far as like, how do I find a power series representation for x squared ln 1 plus x squared? Well, that one is a bit hard, again, because this is even before you do the integral. I'm looking at problem 3 there. You would actually have to first find the power series representation for ln 1 plus x squared. How the heck are you going to do that? Well, you'll have to note that its derivative is going to match one of those forms. Then you'll have to find the antiderivative for that to get back to the ln 1 plus x squared. Then you'll have to incorporate that x squared that's in front of it. And finally, you'll have to integrate the whole thing. So if you followed what I was saying, that's the procedure for that one. It's a hard problem, so I'll warn you right now. Go ahead and try to do 1, 2, and 3 right now. I'll give you 5-10 minutes, and then I'll come back, go through them. Everybody see what happened on that one? If you leave it as -3, 2x to the n, it's perfectly fine. As long as it's an equivalent answer. Okay, so this is what I was talking about with the partial fraction decomposition. Once you find what it is, then rewrite the function in the necessary way. Okay, so that's the two of them separately, right? So basically what we can say then for the whole thing is that putting these two things together, the power series expansion for the given function, this thing, must be these two things to put together. So basically what you can say is this is a negative summation of the two of these things put together. So this is going to be like, what was the first one? Well, let's do it like this. And then notice that you can kind of treat those constants separately. You can factor that x to the n out of there. So you can write this as 1 over 3 to the n plus 1 plus 1, and then factor out the x to the n. And then you could even do a common denominator there if you wanted to and make that constant nicer looking. But anyway, that's good enough right there. Okay, now the question here would be, well, what is the radius of convergence on this one then? For the whole thing, what does the radius of convergence have to be? Remember, we checked the radius of convergence sort of separately for the two parts of it, right? We got those two things. So which one do we need to choose? Yeah, it's got to be one. It has to be the smaller of the two, okay? Whichever has the smaller, yeah, exactly, it has to be the smaller one. So basically, you find the radius of convergence for both parts of it. Whichever one is the smallest one is the one has to be the one for both. Because otherwise, if it's bigger than that, then the first one's not, or the one that has the smaller radius of convergence won't converge beyond, in this case, 1. So it won't converge at 2, where the other one will. So it's got to be the smaller one. Okay, any questions on how that worked? You see the strategy. Find the partial fraction decomposition, and then just do the same thing that we've been doing on the other ones. Change that into some kind of power series representation, and then just put them back together at the end. Okay, anybody figure out that last problem? Number 3, that was a doozy. Working on it. Okay, well, I'll start 2 and then see how you were doing. Okay, so what I did there is I took the derivative for the ln 1 plus x squared, found the power series for that. And so that means the power series for ln 1 plus x squared, since I took a derivative to get there, I have to take an antiderivative to get back. The antiderivative of this thing. All right, so far we've got the power series expansion for ln 1 plus x squared. So that means that x squared times ln 1 plus x squared has got to be x squared times the power series that we just got. How to deal with that now? Just incorporate that extra x squared in there. Okay, boom. So there's the power series for x squared ln 1 plus x squared. Okay, but again, the thing that we're trying to find is the antiderivative of that. So last step here, integral of x squared ln1 plus x squared has got to be integral of this power series that we just found. So our last step here is just to find that antiderivative. And so there it is. That's our final answer for this one. That is the integral of x squared ln1 plus x squared in its power series form. This is another one that would be extremely difficult to find the regular old antiderivative as a regular elementary function. So even though this problem was pretty hard by doing it with power series, it would have been much more difficult to try to do this with any other method. What does that mean? Oh, you have to find c? No, not in this case, because remember that what we're trying to do here is just find a regular antiderivative for that x squared ln1 plus x squared. So we cannot identify that c because we don't know what, like if there were a regular way to write the antiderivative for this function, we could do that, but we can't do that here. For the first what? For the first power series? Yeah, so remember that that's a different situation. Like in the problem where we actually found c, we know what the power series, well, we know what the regular function notation is for the function that we're trying to find, for the power series we're trying to find c for, right? In this case, we knew, like right here, right? This was the function, right? And that thing is centered at 0. So I can plug in 0 for x there, and that's going to be what c is, right? The only way that I could actually find what c is here is if I could find a regular representation for that thing, like in other words, an algebraic representation of that antiderivative. But I can't. So there's no way to find c in this case. And remember, this is just anytime you're just asked to find an antiderivative, like in example 4, go back to example 4. Find an antiderivative, right? That was anytime you find any just general antiderivative, whether it's a power series form or can be expressed as a regular algebraic function. Any antiderivative, you just have that plus c on the end of it. You can't find it, right? There's no way to actually find it unless you have other information, right? Like suppose they told you that, I don't know, whatever that function is, whatever the antiderivative is, if we knew that it passed through a certain point, then we could find c. But we don't know that, so no way to find c here. Okay, so did anybody get that answer? You got that answer. Very good job. Yeah. But were you on the, yeah, the radius of convergence will be the same as what it was for that function up there, where we actually found it way up here. Yeah, right there. Doesn't change by finding antiderivatives. In this case, the radius of convergence doesn't change. So yes, it stays 1. Okay, so did anybody get that problem? Yeah. That was a hard one. That's the procedure, though. That's kind of what you got to think about with these types of problems. You got to sort of take it apart, do part of the problem, figure, how do I find the power series, in this case for ln1 plus x squared. Once I find that, I have to realize that I have to take a derivative to get there. And I got to integrate to get back, and then I got to multiply that by the x squared. Would it be possible to find the interval? Yeah, you could totally find the interval of convergence by using the ratio test in this case. Yeah, you wanted to. Yeah, because this is just now a regular old power series. We didn't get this. Well, actually, by the 2 integrals that we did, we introduced these terms in the denominator, right? Which would probably, in fact, just looking at this, if I think about plugging in 1 or -1 to here, look what kind of a series we're going to get if we do that. We're going to have an alternating series for one of them, and look what we're going to have in the denominator, n squared, right? So even if it's alternating or not, it would compare to a p series with p equal to 2, and I think it would converge on both endpoints. In fact, that's my hunch on this one. It converge on both endpoints. You can kind of glance at it and just see if you plug in 1 or -1, you're going to end up with either an alternating series with an n squared term in the bottom or a non-alternating one that has an n squared term on the bottom. Either way, they'll converge. One of them is a p series, the other one's an alternating series. They'll both converge. Okay, cool. Any other questions? We got to kind of get to this last section here. So what did we think? Was my prediction right that 11.9 is going to be one of the more difficult ones in the semester? Yeah, I figured. This is a very difficult section. Just wrapping your head around what's going on here. It's a lot. There's a lot going on here. Yeah, it's very conceptual, dealing with new material that we've never seen before, power series, infinite series, that kind of thing. Difficult. Doesn't get much easier in 11.10, unfortunately. But maybe a little bit. But this is a really cool section here. This is about Taylor series. If you've heard that term before, what is a Taylor series? Okay, so what they're saying in this section, if you have 11.10 in front of you, you see it says at the top, the form of a convergent power series. It's basically telling you that any power series can be represented in this way. So what I want to kind of do here is just introduce why this formula that you're seeing there. It says Taylor series right there. That's a formula. That formula is actually going to tell you how to find the power series expansion for any function. So notice what we were doing in 11.9 is we were using those two sort of basic functions, 1 over 1 minus x and 1 over 1 plus x. We were using those two kind of in a really extensive way to sort of force other functions to match one of those two things, either by taking derivatives, antiderivatives, or just hoping that it's going to look like that, or partial fraction decomposition, anything like that, right? What about functions that there's absolutely no way to do that, right? Like if you think about the sine function or the cosine function, there's really no way, derivatives, antiderivatives, that you're going to make it look like 1 over 1 plus x or 1 over 1 minus x, right? That's just not going to happen. And so what we do in 11.10 here is we come up with a way to find a power series expansion for any function, regardless of what it looks like, okay? And so what we first start out with is this idea of a Taylor polynomial, okay? Taylor polynomial. And so what the idea here is that the thinking is that you want to be able to approximate a function with a polynomial function. In other words, is there a way to do that? Is there a way to just take any old function and say, well, let's see, can I make this function into a polynomial? Or at least get it to kind of match a particular polynomial, pretty closely for some interval. Okay, and so that's the goal. We would like to take some function, f of x, in fact, let me just insert that in there, and approximate it with a polynomial. So in other words, this is what we would like to do. We would like to take a function f of x and figure out its polynomial approximation. And I'm going to put a squiggly equal to say approximately equal to an nth degree polynomial. We're going to abbreviate that as p sub n, or nth degree polynomial. Okay, that means it's a finite degree polynomial. That's important for us to think about. It's a finite degree polynomial. So in other words, suppose I was saying, well, is there a way to approximate the sine function and say that it's going to be equal to some, or approximately equal to some 10th degree polynomial, or 20th degree polynomial, or whatever. So how would we go about doing that? Well, let's first of all notice what a nth degree polynomial is, what it looks like. Well, it would look like this, right? You'd have a constant term. I think they're using the letter C here. You'd have a constant term, then you'd have a first power term with some coefficient, and then you'd have a second power term with some other coefficient, right? And so on. And so this would just keep going. I'm going to write out about 4 of them, I guess. It's probably going to be enough. By the way, this one is going to be centered at 0 because I'm putting that just the x. If you see If you call it x minus a, then it's centered at a, but everything that I'm saying here can be extended to it being x minus a instead of x. So for right now, we're just going to focus on centering it at 0. Okay, anyway, then this is going to come up to some n minus 1, and then x to the n minus 1. And then the last term on this nth degree polynomial will actually be the nth term, right? The nth power on it. Okay. Questions so far about what we're doing? This is just saying that's what an nth degree polynomial is going to look like. Yeah. Okay, so the goal again is to try to make this function match this polynomial, okay, as closely as possible anyway. Well, let's see, what would be a good thing to happen to make a function be the same or at least pretty close to a polynomial function? Well, let's see, it probably would help if when you plug in the center, that you get the same output value whether you plug it into the function or whether you plug it into the polynomial, right? You probably will want both of them to have the same output value, right? That's pretty reasonable. If you're trying to get a polynomial to approximate the function, you probably want them to have the same output value, yeah? So in other words, for that to happen, we would have to say, let's see, if I plug in the center, f of 0, I would probably want that to be the same as when I plug 0 into the polynomial approximation, right? But what is Pn of 0? Anybody see? What's Pn of 0? Yeah. Specifically, it's this constant, right? C naught. Everybody see that? Because what I'm doing is I'm plugging 0 in right there, and then all the x's, right? All the x's are going to get zeros. Everybody see that? The only one that doesn't go away is that, the constant term. Agree? Cool. So that's okay. Another thing, just to clarify a little bit here, we are trying to determine what these coefficients are, because if we can identify what those coefficients are, all of them, then I will know exactly what that polynomial has to be, right? I mean, a polynomial is actually determined by its coefficients, is it not? What all those coefficients have to be. If those coefficients are all known and all determined, then that polynomial can only be one thing, right? Whatever those constants happen to be. The goal here is to try to figure out what those constants are. Well, look what we just did by saying that the output of the function has to be the same as the output of the polynomial. We've just identified what that first constant has to be, right? That first constant had better be whatever the output of the function is at 0, at the center of the polynomial. Okay, that makes sense? We've just identified the first constant. That's what it has to be. Okay? C naught. Okay, well now, just as we would like the two functions, the original function and the polynomial approximating function, to have the same output value, it would also be helpful if they had the same slope. We agree with that. So function and approximating function should probably have the same slope at the center, yeah? And so what is the slope? Well, that's the derivative of the function, right? And so we would probably also like f prime of 0 to be equal to f prime of, or sorry, not f prime, but p prime of 0. So now to do that, I'm probably going to need to know what p prime of n is. So let's do that. P prime of x. What is p prime of x? Well, again, I'm looking at this function up here. What is its derivative now is the question. Well, let's see, the derivative, the constant term is just going to go away, right? So I'll be left with c1 plus 2c2x plus 3c3x squared plus 4c4x to the third, and then plus, and then this is just going to keep going. And then I'll have n minus 1, whatever that is, c sub n minus 1, x sub n minus 2, and then plus n cn x to the n minus 1. Okay. Everybody see what I just did? I just took the derivative of p sub n of x. Okay, so that means, what do we want? We actually really want this. But again, if I plug in 0 for all these, what's going to happen? They're all going to go away, right? And so there we go. C1 has to be equal to, and then if you kind of come back up to 2 steps above that, that's telling us that f prime of 0, that is what has to be our C1. Okay, so now we've just identified 2 of the constants in this, that one and that one. C1, whatever that C is, that C1 is going to have to be equal to the derivative of the function when we plug in 0 to that. Okay. Yep. Cool. So now you probably are getting the sense that we're also going to maybe need a higher derivatives as well. So we're going to also need the second derivatives to be equal. So let's just find the second derivative of this polynomial. Second derivative is going to be 2c2 plus 3 times 2 c. I'm not going to multiply it out, and we'll maybe see why in just a second here. 4 times 3 c4 x squared, and then all this is just going to keep going, and then we'll have n minus 1, n minus 2, c sub n minus 1, x to the power of n minus 3, and so on and so on. So n minus 1, c sub n, x to the n minus 2. Okay, so that's the second derivative, and so again, we're trying to make sure that this, the function and its polynomial approximation both have the same second derivative now. So in other words, we would like the second derivative at 0 to be equal to the second derivative at 0 of the polynomial. And now that I've written out that second derivative, again, those x's, when I plug in 0, those are all going to go away. And I'm going to be just left with 2c2 now. And so this is telling me that c2, that second or that third constant, has got to be equal to the second derivative evaluated at 0 divided by 2. I'm going to do one more of these to try to see, so that you can maybe see the pattern here. Oh, maybe 2 more actually. Yeah, starting to see a pattern. Good. Let's see what the third derivative is. The third derivative is going to be 6, or 3 times 2. Yeah, let's just call it 6. 6c3, and then the x is gone in that case, and then we'll have 4 times 3 times 2 c4 x, and then let's keep going, and then we'll have, these end ones don't really matter too much, but I'll just write them anyway. Okay, and so then again, what we want to see is we want the third derivative at 0 to be equal to the third derivative of the polynomial at 0. And then again, if you look at the third derivative, the only term that's left after you plug in 0 there is just going to be that 6. So we're going to get 6c3, and so that tells us that the fourth coefficient of this polynomial had better be equal to the third derivative of the function evaluated at 0 divided by 6. Remember that 6 was 3 times 2. Okay, now I think the pattern might be emerging here. So let's see what happens if we try to find the nth derivative of this thing. Does anybody see what the nth derivative actually is going to be? Well, isn't that just going to be n factorial? You see the factorial pattern emerging right there? N minus 1, n minus 2. You see that? And then what we want to have happen is we want that nth derivative to be the same when we plug 0 into the nth derivative of the function. So we want that to be equal to this. And we just said that that thing was n factorial d sub n. So that's telling us that the nth coefficient on this thing had better be the function, the nth derivative of the function evaluated at 0 divided by n factorial. So we have identified every single coefficient now, all of them, for this polynomial function. And so what we can do now is put this all together and say that this function can be approximated by an nth degree polynomial that looks like this. Oops, let me I. I think that should say 0, not 1. It should say I equals 0. Okay, so there it is. That's the formula for the Taylor polynomial, the so-called Taylor polynomial function. Okay. This will allow us to find the Taylor polynomial for any function that would be could be then approximated. Actually, I shouldn't say any function. I should say any function that has infinite or n many derivatives that are defined. Because if you don't have, that's not f to the power of I. Remember the notation for the higher derivatives than the third derivative? We put that, it kind of looks like an exponent, but it's not. If you say f, it kind of looks like a power, but it's in parentheses. That's the important thing. The parentheses signify that you are actually talking about an nth derivative there. So the way that we would read this formula is f of x, and I put an equal to, I shouldn't have put an equal to, I should make that an approximately equal to, is approximately equal to the summation of the, this is f, the ith derivative of the function, evaluated at 0, divided by I factorial, and multiplied by x to the n. Now, you can write that out. Look what happens when you start writing out terms. When you plug in 0 there, first, the bottom index, right? What do you get? You get f 0th derivative. But what's the 0th derivative of a function? It's just the function itself. 0th derivative is just the function itself. And then you'd have x to the 0 power. And so you'd see that it's just f of 0 right there, right? And that's exactly what we said the C naught term has to be. It has to be f of 0. Okay. Then when you start plugging in 1, you see that you have the first derivative evaluated at 0, x to the first power. Then it's 2, then you're going to have the second derivative evaluated at 0 divided by 2 factorial, x to the second power. This is exactly what we have written up here for all these C sub n terms, all these coefficient terms. All right, so if you follow that, good job. This is just kind of the approach, right? This is telling us how we're getting to this point. It's nice if you understand that, but really for what we're, the purposes of what we're doing here, it really doesn't matter that much if you follow exactly everything that I just said right there. All I was doing there is deriving this formula, okay? Okay, now we're going to take this one step further. We're going to say that is a Taylor polynomial, okay? That just means that this is going to approximate the function, okay? Well, what if we decide, well, what if I want this Taylor polynomial to now be a Taylor series? In other words, not just a finite degree polynomial, but an infinite degree polynomial, right? What if I want that to happen? In other words, what if I take the limit of this as n goes to infinity? Well, it turns out if you do that, then you get what's called a Taylor series. And at that point, when you find the Taylor series, then you can replace this approximately equal to with exactly equal to. And so this gives us the formula for a Taylor polynomial, an infinite degree polynomial that exactly matches the function that it is attempting to not approximate anymore, but be equal to. So this is exact equality now. This is the formula that will tell you how to find the Taylor series expansion for any function that has infinite, or that has infinitely many derivatives that are defined, such as, for example, sine and cosine and stuff like that. Okay. I know this is pretty dense stuff here. Now, if you notice, and I'm not going to spend very much time on this, but just if you kind of look down there where it says Taylor polynomial, we said that's the nth degree Taylor polynomial of f at a. Yeah, for one thing, these are all centered at 0, by the way. If you want to center them somewhere else, all of this stuff still applies. Everything that I just said still applies. The only difference is that now you center it somewhere else, like at a. And then this has to be an x minus a to the n. Okay. So, in fact, this one is given a special name. It's called a Maclaurin series. And this one is called a Taylor series. Kind of weird that they have different names, because really the Maclaurin series is just a special case of the Taylor series, if you see what I mean. What's the special case? It's the case where a is equal to 0. If that makes sense. So I guess they figured they wanted to give this guy Maclaurin credit for something, so they named the one that's centered at 0 after him. The ones that are centered anywhere else, they're named after Taylor. All right. So now, if you notice, sort of at the bottom there, it says the Taylor polynomial. There's a little bit of extra stuff on there. It's talking about the remainder. That thing that they're calling r sub n of x. Well, remember that thing that was a Taylor polynomial was just an approximation. And so what's the difference between the exact value of the function and the approximation of the function? Well, it's this thing that they're calling r sub n. And if you can kind of see what this is saying, this is the remainder. This is the actual function, right? And that is the Taylor approximation of the function. So clearly, since it's an approximation, these two things are not quite equal to each other, right? So the difference between them, whatever that difference is going to be called the remainder, okay? And so ideally speaking, what do we want to be true about that remainder? Well, we'd like the approximation to be as close to the function as possible. So what would we like to see that remainder be? We'd like to see that to be as small as possible, right? The remainder needs to be as small as possible. And so what they say about this Taylor series, the Taylor series, this thing up here, is, and the Maclaurin series for that matter, for these, what should be true about that remainder, Rn? Since we have not approximately equal to anymore, but it's exactly equal to, what should be true about that Rn? Anybody? Should be 0, exactly. And so what they sort of go on, and they spend a bit of time in the book sort of harping over this and saying, we really want that Rn to be 0. And they sort of go through all this stuff about saying why it is going to be 0. For the purpose of what we're doing here, I'll just tell you, it's going to be 0. So when we're talking about a Taylor series, we don't really worry too much about that R sub n. They actually go through and, like I say, go to pains to show that, in fact, it really is, or it does go to 0 as n goes to infinity, as the number of terms of the polynomial goes to infinity. So for purposes of what we're doing here, just take it on faith that R sub n is going to be 0 when we're talking about a Taylor polynomial. Okay? All right, now, one thing, let's go ahead and try this stuff about how we use this formula to find a Taylor series. Before we do, are there any questions? Okay, so we only have about 15 minutes. I do want to at least get a couple of these examples. Let's do example 1. Okay, now this function should look kind of familiar. We've already found a Taylor series expansion for that. However, notice that this one, they say they want to evaluate it when c is equal to 2. In other words, they want it to be centered at c equals 2. Yeah, centered x equals 2. So that means we're trying to find a Taylor series expansion for this thing evaluated at 2. So that means, let's see, I'll come back up here. We're trying to do this. F of x is equal to this formula. This is the formula to find the Taylor series for any function. But since we're doing this at 2, this is what I have to put the 2 right there. And then I also have to put an x minus 2 here to the n. Okay, so that's the formula we're trying to find. Okay? All right, now how do we do this? Well, the goal is, what we're really trying to do here is, the only thing that depends on the particular function that we're looking at is just this. Right? No matter what the function is, all of the rest of this stuff just stays the same, doesn't it? I mean, this would be the same no matter what the function is. You guys agree with that? That stuff does not change. Okay? We are only trying to find the stuff that's circled in red there, or boxed in red there. So let's do that. How do I find fn of 2? Well, it would probably help by finding f1, the first derivative, and the second derivative, and so on. So if this is the function, 1 over 1 minus x, then maybe you might want to write it like this to help take derivatives. Then let's see, first derivative. First derivative is going to be negative 1 minus x to the negative 2. And then we're also going to need another negative because of that chain rule, right? And so this is going to end up being 1 minus x minus 2, or just 1 over 1 minus x squared. Okay. Second derivative. Well, let's see, that we could just probably look at that term right there and figure out what that is. It's going to be minus 2, 1 minus x to the minus 3. But then we're still going to have that other minus 1 there. This is the chain rule again. And so eventually we'll probably start seeing that there is a pattern here, right? This is now 2 over 1 minus x to the second power. Let's do one more, and maybe we can establish what the pattern is after we've written about 3 of them down. What is the third derivative here? Well, it seems like if I take another derivative, I'm going to have that 3 is going to come down, so I'll have 6 times 1 minus x to the minus 4, and we know that that's just going to, chain rule is going to take care of all the negatives on this, so I'll have a 6 there. Oops, I think I copied that one wrong. That should have been the third power, not second power in this one here. Sorry about that. Should be 3. Okay, I'm just going to do one more just so that we, yeah, thanks. Just so that we get very clear on what the pattern is here. Fourth derivative. 6 times 4, that's going to be 24, and then 1 minus x to the minus 5, so we'll have 24 over 1 minus x to the fifth. Okay, now this has got to be enough to figure out what the pattern is. What the goal is, I want to figure out what is the nth derivative. Can we get a formula for the nth derivative here? In this case, I think it's pretty clear. Well, maybe not entirely clear, but pretty close. Let's compare a few things here. We are on the fourth derivative here, right? And that number there, what is that number? Isn't that 4 factorial? Isn't that 4 factorial? So isn't it? Yeah, I think, Joseph, you're on the right track there. That's the fourth. That's 4 factorial right there, right? And we're on the fourth derivative. This is third derivative, and that's 3 factorial, right? So when I'm looking for the nth derivative, I should expect to see the nth factorial right there, right? Pretty clear? And then look at the denominator. 1 minus x to the what power? I'm on the fourth derivative, but that has a fifth power, right? N plus 1 right there. That makes sense? Just notice that whatever derivative we happen to be on, that power that shows up in the denominator is 1 more than that derivative that we're on. See? Okay, now what we're really after here is what is f, the nth derivative, evaluated at 2, because that's what we're asked to find, right? The nth derivative evaluated at 2. So how do I find that? Well, I just plug in 2 for x. And so that gets me n factorial over 1 minus, so that's negative 1 to the n plus 1 power. Now, whether I put the negative 1 to the n plus 1 in the denominator or the numerator, it's the same thing, because all it does is just end up alternating the terms. And so I can write it like that too if I want to. That makes sense? So what is our Taylor series for this function then? It should be the sum to infinity. I'll just go ahead and write this all out again so we can have to scroll up and down. This should be the nth derivative evaluated at 2 divided by n factorial, and then x minus 2 to the n here. And like I said, the only thing that really changes as far as what the actual function is that numerator. We just found that numerator, right? Didn't we just do that? Fn of 2, boom, right there. That's what it is. Oh, you see? There it is. That's what we're going to be replacing now. That is negative 1, the n plus 1, n factorial over, and we've got another n factorial here. And then we've got x minus 2 to the n. So see what happens with this? Those cancel. And so now we're left with this. Negative 1 to the n plus 1, x minus 2 to the n. So that is the Taylor series expansion for this particular function, 1 over 1 minus x, centered at x equals 2. Now, one other thing I just want to show you, we've got about 6 minutes. Now remember, we could have also done this problem by the methods of section 11.9. So quickly, by the methods of section 11.9, what would we have done differently here? Well, if I wanted to center it at x equals 2, I would have had to change this to make it do this. Have a minus 2 there, right? And then remember this, I think I did one example like this. And then, of course, I can't just change the function like that. I have to put x minus 2 plus 2, and then I can go like this, and I can say 1 minus x minus 2, put that in parentheses, distribute the other 2 over there, and then this becomes 1 over, let's see, that's going to be 1 minus 2 minus 1 minus x minus 2. And then notice that you can actually factor a negative out of the denominator and put it in the numerator and get 1 plus x minus 2 there. Now, by the methods of the previous section, that should be the same as this. And since it's a plus down in the denominator, we'll have a minus 1 to the n there. And then we'll have an x minus 2 to the n. Okay, now finally, just notice that negative 1 in the front can actually be incorporated into the to the n right there, right? And so that can then be written as this summation, negative 1 to the n plus 1, x minus 2 to the n. So my point here is what I want you to see, what I want you to notice is that whether we use the techniques of chapter or section 11.9, we get that answer, or we use this new technique of finding the Taylor series expansion with that formula, look what we get. The same answer, right? The same answer. Does that make sense, what I'm showing you here? So, I know this is probably somewhat overwhelming, I would imagine, right now. If I were saying this for the first time, I would be pretty lost, I think. Any questions about this? Yeah, I mean, it's hard at first, but when you realize what you need to see in a denominator, you kind of have to figure out what do you have to do to make it produce what you want, to match that 1 over 1 minus something formula, 1 over 1 plus something formula. Yeah, it just takes practice, really. Okay, that other problem is actually pretty quick, and I think we can probably get it done in 3 minutes. So let me just go ahead and do that so we can see one more of these. So let's look at that B problem there. So again, the goal is to try to find a Taylor series expansion for this function. In this case, it's centered at 0. That's kind of nice. It's equals 0. So if you remember the goal, or let's try to figure out what we're doing here since we've only seen one example. The goal here is to try to find a formula for what we want to find. In other words, a formula for this. The nth derivative of the function evaluated at 0 in this case, because this one's centered at 0. And the last one we wanted to evaluate it at 2. So this function is pretty easy to differentiate, right? Just minus 4 e to the minus 4x. And every time I take another derivative, second derivative, I'm going to have another minus 4 on there because of the chain rule, right? So minus 4 squared. Notice I'm on the second derivative, and then the third derivative. I'm going to have another minus 4 on there, right? Everybody following just from the chain rule? And so if we kind of establish what the pattern is here, can we come up with a formula for the nth derivative? Well, again, notice that we're on the nth. We're on the third derivative produces -4 to the third power, and so the derivative that we're on seems to match the power on the 4 that we're getting. It's -4 to the n, and then just that, right? But again, the thing that we really are interested in is what is this when we plug in the center, right? When we plug in 0, what do we get? When you plug in 0, you just get e to the 0, which is just 1, and so we're just going to have -4 to the n, right? And so when I want to find the power series expansion for e to the -4x, again, by this formula, the formula is we need to come up with a formula for the nth derivative, in this case evaluated at 0. N factorial stays the same. X to the n stays the same regardless of the function. Now we've got that formula, right? We have that formula for the nth derivative. Now I'll just plug it in there. -1 to the n, 4 to the n over n factorial, and x to the n. So there it is. There's our power series expansion for e to the -4x. Any questions about that one? I notice this is another one that could not have been done by the method 11.9, right? The last problem was possible to do that because it was, well, exactly what we wanted pretty much. This one could not have been done by those techniques because there's no way to take any number of derivatives and get it to look like 1 over 1 minus x or 1 over 1 plus x. You can leave it as -4 to the n, but it should be parentheses around the -4 if you do that. Okay, well, we're out of time. So yeah, that's right. So we're gonna we have to do, what else do we have to do here? Yeah, there's just a couple of other things that we need to take care of on this. In fact, I might skip a couple things like the binomial series, and yeah, but for the most part, we're making good progress on this section. We just have to do a few more. In fact, if you notice, there's no problems to do for you guys. It's all just examples. So we'll finish this up next time, and then we'll review for the test next time as well. That test, by the way, that's another one that I've made, I think, if I remember correctly. If you go on to CNM Learn and you look on the tests or the exams link, there should be the practice exam 3, I guess, and I think if I did that, I don't know if anybody's checked this, but this one should also have a bunch of links on it to video solutions that I've done for the second exam. I'm actually going to change that a little bit to, well, yeah, there's a couple of other things I need to put on there, but yeah, if there's links there, they should work because they're just taking you to YouTube videos that I made. So, so yeah, if you want to start looking at the practice exam, all those things have video solutions on them, and in fact, for that reason, I might not get through the entire practice exam. I might just leave it up to you guys to watch some of those videos. We'll see how far we get on finishing 11.10 next time, and then also starting the review. But we'll try to get through as much as possible. Anyway, we're at overtime now, so If anybody has any questions right now, I'd certainly be happy to answer them after class. But you're welcome to leave now. If anybody has any questions, I'll give you a few seconds to ask. And if not, we'll see you guys next time. Yeah, the exam is scheduled for next Tuesday. And we're going to stick to that for now, unless I decide we'll change it. But I'll let you know next time for sure. Yeah, I have my office hour today is as usual, 5 o'clock. Today's Tuesday, right? Yeah. And then I have an office hour tomorrow as well, marked on the syllabus. I can't remember exactly what it is, but whatever it says on the syllabus, I'll be here on WebEx as usual. So if you need help in office hours, I'll be here at normal times. Cool. If there's nothing else, we'll see you guys on Thursday.